All right, let's get started. I didn't mention this last time, but considering the sheer volume of people in the room, I guess we'll just have to make sure that appropriate hygiene protocols are taken into account. That was a joke, not a very funny one. I know, it was. I don't really have much in the way of major announcements because same as before. Again, I'll be canceling class next Wednesday, and then your first homework will be on Friday. It will be due not Monday, but the following Monday. And it's a pretty straightforward assignment. It's pretty short. I know the folks in concrete design have one as well, but it's all load stuff, so it all kind of goes together. Other than that, I really don't have much in the way of announcements. We're just going to continue our discussion of loads. And last time, I think I spent a lot of time talking, and I'd like to get to doing today and doing some examples. So we're going to look at doing some examples with lateral load effects. We've got some wind, some seismic effects, and we'll see where we get, but probably between today and tomorrow, we'll pretty much finish wind. And then when we get back from next week, so after this week, we won't see each other until the following Friday, but we'll probably start breaking out the manual. And I know definitely into week 3, if you don't have the manual, you'll want to start bringing it. So, sound good? All right. So, let's see. Okay, I'll go back a couple slides because we got time. So, and plus, I can't help but show the dog again. Okay, so if you recall, last time what we were sort of doing was looking at structural engineering responsibilities, kind of from a 30,000-foot view, you know, what our responsibilities are in a given project. And we sort of recapped some things from concrete design, like load factors, why we're doing LRFD as opposed to ASD, and what have you. And then we started to get into some specifics regarding loads. Remember, in concrete design, we handle gravity loads, and in here we handle lateral loads, so that between the two, you kind of have a general idea. Now, just so you are aware, what we are doing with lateral loads in here is very sort of watered down. There's a lot of different, you know, specific issues with wind, with gusts and eccentricities and all sorts of different things that we really don't have time to cover in here. But I at least want you to be somewhat familiar with the basic provisions, and so that's really all I'm going to require. Like I said, there's really only 2 lateral load events that we handle, and that's wind and seismic, so we'll take those one at a time. Remember, we don't design the entire building to withstand lateral loads, but we design a certain component of the building to withstand lateral loads. Just like the dog in the seat belt, instead of designing the entire car to hold the dog back, we install a system to hold the car back, or hold the dog back, and we call that system a seat belt. So the seat belt's job is to withstand that lateral force effect. It's not the whole car, it's just the seat belt. Just like in a structural steel frame, it's not the entire frame's job to withstand wind and earthquakes. It's a specific component of that frame. Now, we really have 2 primary systems that we use. We have braced frames, which again is actually inserting bracing elements into the system. So when it's all said and done, braced frames behave a lot like trusses. Basically, what you're going to do is once you determine your equivalent wind pressures on the building, you take those wind pressures and that whole tributary area concept, remember that? You take that tributary area concept and distribute those pressures as point loads on the brace frame, and then you're basically doing a truss analysis in order to determine, okay, what's the tension in this brace, what's the compression in this brace, and then design accordingly. So that's what a braced frame is. A moment frame is basically where you're just using rigid connections between your beams and columns in order to resist those loads. Moment frames tend to be a little bit more flexible, like they allow a little bit more sway. So if you had the exact same building, let's say you had the exact same building, you know, 2 buildings side by side, one had a brace frame and one had a moment frame. The moment frame would want to move more under the same event. Usually moment frames are a lot more flexible. But there are some advantages. Again, you have open spaces, so it makes it easier to navigate the building. And if you're designing a building, you want to make the architect and the client happy. So there are trade-offs, but it's just, it's whatever, is appropriate for your given project. Again, you need to be able to assess both. So we'll start talking about wind loads. I think I went through this kind of quickly last time, so I want to take my time and go through it in a detailed fashion. So again, one of the reasons that lateral design is so complicated is, at least with winds, is that wind pressures get larger the taller the building gets. So, your wind pressure and your design for wind is a function of height. In fact, the height of a building can dictate what the building even looks like from square one. Again, gravity loads, a floor beam on the second story is the exact same as the floor beam on the 82nd story. I mean, the design process is exactly the same when you're looking at gravity loads. But lateral loads, it's a little different. The wind pressures get higher as the building gets taller. The wind pressure on Smith is different than the wind pressure here, because that building is a lot taller. So it's just something to keep in mind. There's a reason why, for instance, what's the Burj Khalifa, the tallest building on the planet? There's a reason why it's kind of conically shaped. You notice it's kind of shaped like a cone, kind of. That's because it dissipates those wind forces a lot better if the building is that shape. There's a reason for that. So it's just something to think about, large scale, type things. Okay, so here's our fundamental base wind pressure equation. Again, this is just Bernoulli's equation rearranged for elements that are at the same height, so your elevation head is gone, and then all you do is you take in the unit weight of air, you plug in a unit conversion to convert wind speeds that are in miles per hour into a pressure that's in pounds per square foot, and so that's where that 0.00256 comes into play. It's just Bernoulli's with a unit conversion in it. So you have point A with a velocity and no pressure, and then point B has no velocity. What's the pressure at point B? So it's just Bernoulli's equation. It's pretty straightforward. And then we take that Bernoulli's expression, and then we adjust it with a few modification factors. So we adjust it with a topographic factor, which in most cases is usually 1, and we'll take it to be 1 in here. If it's not 1, it's a lookup and a pretty basic formula. K sub D is a wind directionality factor, and for buildings, that's always 0.85. That's a lookup as well. The only thing that's not really a lookup is the KZ. That's the exposure coefficient, and that's how you change your wind pressure as a function of height. As your Z gets higher, your KZ value gets larger, and so that's how your wind pressure equation changes. Now, your base wind speed is a function of your risk category. I think we discussed risk categories last time. Your risk category is essentially a definition of what your building is being used for. If a grain silo or a barn or an unstaffed warehouse falls down, that sucks, but it's not really going to pose much of a risk. Whereas a police or a fire station or a 911 call center, if that structure fails, yeah, that's a problem, because that affects not just them, that affects everybody. So the risk category of your structure is contingent on what it's being used for. Excuse me. Now this term K sub Z, it's a pretty basic computation. If you have experience in Excel with using the if function, this is pretty easy to set up. If not, you can just compute this, by hand. It's pretty straightforward. So again, the exposure constant changes as a function of what your Z value is. If Z is less than 15 feet, it's a constant value, and if it's larger than 15 feet, it increases sort of parabolically. If I go back a couple slides, so this is an image of wind pressures on buildings, and if you notice right here, it's sort of like a constant wind pressure, and then it gets larger. Basically, in structural engineering land, what that means is we just assume that if you have a short building, anything lower than 15 feet, we just say, okay, let's just use a constant pressure. But if it gets taller, then we have to adjust accordingly. So that's a pretty straightforward computation. So again, it's pretty plug and chug. So it's a function of the height of the story, and it's a function of two parameters, a gradient height and an exposure constant, and that's dependent upon your exposure category. Now there are three exposure categories in the spec, and this might give you a little bit of insight into sometimes how specs are written and how sometimes it's kind of weird. There are three exposure categories, B, C, and D. Where's A? Well, there isn't one, not really. There is an exposure category A, but it's only used in the spec as a reference for when you have to do wind tunnel testing. And you're only going to do wind tunnel testing if you got a really unique structure, like a really tall structure or what have you. The spec actually allows you to build sort of a scale model of your structure and instrument it with strain gauges and whatnot and put it in a wind tunnel and then measure the strain and say, okay, well, that's my forces on the building. And you can do that, but it's pretty expensive, and you would never do it unless there's a reason to do it. If you're doing a regular old everyday structural design, you're never going to do that. If you're doing the Burj Khalifa, yeah, you're going to do wind tunnel testing. So it just depends on your project. If you have something really weird, you go forward and do that. But the spec has three exposure categories defined. It just depends on where your building is. Mostly, as a structural engineer, I'd say you're probably going to be dealing with either exposure category B or C. Exposure category B is if you're in an urban scenario, whereas exposure category C is a little more rural. And think, if you're designing for wind, well, it'd be different designing for wind if there's stuff around the building. That's basically what the exposure categories are trying to capture. If you're designing a building in the middle of Manhattan, well, there's a bunch of other buildings around it. So the wind forces on that building are going to change because there's stuff surrounding it. Whereas if it's a building out in the middle of a farmland, well, there's nothing preventing the wind from hitting it. So does that make sense? That's a good question, and I'd say what's going to happen in those scenarios are really one of two things. One, you might have to encounter wind speed-up effects depending upon the topography, like if you have a building on top of a hill and you have wind speed-up effects. And there's rules in the spec for when you need to account for that or not. And two, whenever you have a special wind region. For instance, I'm from Bluefield, and there are areas in the Bluefield, West Virginia area that are counted as special wind regions because you're basically in one big valley, so it changes. I'll say this, in this area, like in Huntington, like if I was designing a building in Huntington, I would probably go with exposure category C. This isn't Manhattan, but that's me. What do you mean?
Where the wind is getting forced through the smaller space.
Well, it can, but that's usually not the issue. The issue in a place like Manhattan is just the buildings are really tall. And so the wind forces just get really, really large as the building gets tall. That's really the issue. How many of you have ever been to like New York? Have you ever been on top of that deck, the Empire State? Anybody been outside on it? What was your experience? It was really windy, wasn't it? That's because you were really high up. So that just happened. So yeah, that's a good question. Any other questions? Okay. I want to look at an example. So we're going to determine the base wind pressures for each of these stories in a regular commercial office building in Huntington, West Virginia. Now this office building, I'm looking at example 1A. We're going to kind of refer to this same building later when we look at seismic. So the dimensions are pretty similar. But I have a building that has a series of story heights, and the story heights are varying for a specific reason. But we're going to assume that this is a structure of risk category 2, and we're going to assume that it's exposure category B. And I'm just doing this for the sake of computation. and we're going to take KZT equal to 1. So what I want to do is I want to determine the base wind pressures at each story. And so in order to do that, I'm going to have to compute, a series of KZ constants, which is pretty straightforward, but I also need a base wind speed. So how am I going to determine the base wind speed? Well, I can go off the ATC Council maps. So let me, first let me go to the web. So if you recall, one of the things I can do is I can go to Google and I can say, okay, what's the latitude and longitude of Huntington, West Virginia? And honestly, I kind of prefer to use latitudes and longitudes for a lot of this stuff, especially if you're designing a new building. If it's a brand new building, does it have an address? It doesn't exist, So I tend to use the latitudes and longitudes because every location on the planet has a latitude and longitude. So that's just me. But I know I'm designing the building in Huntington, West Virginia, so I look up the latitude and longitude for Huntington, West Virginia, and here's what I get. So I go to the hazards map, hazards.atcouncil.org, and then I put in the latitude and longitude that's reported. Remember, the west coordinate is negative because on the x-axis that's negative. And then it says, okay, here's Google Maps, and there's the wind region. And so let me zoom out a little bit to sort of show you. So you can see a couple things. So for instance, here, let me zoom out a little further. Oh, goodness. So you can see here's the wind speed map in the United States. And basically what it's doing is it's sort of identifying where you fit within the wind speed map. One of the things I mentioned, see this sort of shaded area right here? This is the special wind region I was talking about earlier. So again, like I said, I'm from the Bluefield area. So there are some areas in that surrounding area that can be considered a special wind region. But long story short, we're in Huntington, West Virginia, and it locates what is the hazard, what are the environmental hazards at that latitude and longitude, and it reports wind speeds for design. Now, just so you're aware of what we're seeing here, there's a series of wind speeds that are being reported. There's the first 4 are called MRI, 10-year, 25-year, 50-year, 100-year. MRI stands for mean recurrence interval. And basically, you can sort of think of this, remember like the 100-year flood, 50-year flood, remember that? This is sort of the 10-year wind, the 25-year wind, the 50-year wind, the 100-year wind. And so basically what the spec body has done, and this has changed from edition to edition, but what they've done is because LRFD is becoming the norm, they reported these wind speeds such that they're already factored. Like if you look at the LRFD load combinations, the load factor for wind is 1 because the load factors are sort of already built into the load. So LRFD really is becoming sort of the way to go. So much so that we have different wind speeds recorded for different risk categories. And like I said, they've really already been factored. So risk category 1, risk category 2, risk category 3, and risk category 4 for this region. If we're using risk category 2, that's a wind speed of 106 miles per hour. So that's our maximum, if you will, factored design wind speed. So that's going to be our V, our velocity for this problem. So somebody remember that, 106. Okay. Now, I like doing this. Sorry, I just think that's cool. Okay. So here's our building. Okay. So let me know if you have issues reading this or whatnot. This is my first time really using this software for lecture and whatnot. So base wind speed. So we have a V which was 106 miles per hour, and that's risk category 2. Okay. Now, remind me, we have, what's our exposure category for this problem? Exposure category, nope, category, not category. So if we have exposure category B, we have ZG value that we're going to need, and an alpha value that we're going to need. What is ZG and alpha? 1,200 feet, and we have alpha, which is 7.0. Okay. Now, also for this problem, we know that KZT is 1, and we know that our wind directionality factor is 0.85. Sound good? Okay. Now, what I'm going to do is I'm going to consider like one story. I'm only going to do this for one story, and then I'm going to pull up an Excel file that I posted on Blackboard that should make it a little easier to do the others. But before I do that, one of the things I want to make sure that everybody's clear on is how to express and how to compute the elevations. Okay, so here's the building. Okay, and so what we're going to need are Z values, and Z is measured from the ground. So I propose at the very bottom right here, Z is 0. Okay, so that's Z for the ground floor or for the first story. Okay, and that can usually get a little confusing. Like, is the ground floor the first story, or is it ground then first then second? Which is why I just usually say, okay, that's the second story. I label it. So, all right, so this is Z equals 0. So for the second story, this is Z equals 12. So what is Z for the third story? 26. This is Z is 26. What about for the fourth story? 41. And what about Z for the roof? 53. Everybody okay with that? Okay. So if we consider, for the sake of discussion, let's consider the fourth story. Okay. So consider the fourth story. So we have a Z value of 41 feet. Okay. So if we have a Z value of 41 feet, let's go back to this. Okay. So we have basically two quantities to consider. We have we have KZ is for when Z is less than 15 feet or when Z is greater than 15 feet. And so that exposure category basically says that this expression would be valid anywhere from KZ, or from a Z to 0 to a Z of what, 1,200 feet? So that's pretty tall. So are we going to use the upper expression or the lower expression? Upper. Okay. So therefore, come on, KZ is 2.01, and that's Z over ZG, and that is raised to the Z over alpha. Okay, or no, 2. Why not 2? Okay, so that 2 over alpha, that is the exponent. So it is raised to 2 over alpha. Okay, so that is 2.01 times, and then we have 41 feet over 1,200 feet raised to the 2 over 7. Okay. I need a value. It means, oh, it's the second. Do we really have to break out calculators? Yes, we have to break out calculators.
This is the first example I have here.
0.766. Yeah, and so 0.766. Everybody okay with that? All right, okay. So that's the KZ quantity. So therefore, Q QZ is 0.00256, and then it's times KZ, KZT, KD, V squared. And then the way this works is you plug in a velocity in miles per hour and you will get a pressure in pounds per square foot. That's what this is doing. This is sort of your unit conversion, if you will. I say sort of because there's a little bit more going on with Bernoulli's. So 0.00256 times 0.766 times 1.0 times 0.85 times 106 squared, and that comes out to what? Say it again. 18.73 pounds per square foot. Do I have a second on that? Okay, that's it. So that's your wind pressure on the building at that story. Okay, so you're going to have different pressures on the building as a function of height. Okay, now that's just for one story. You could probably see how this calculation would get repetitive if I had a building that was 20 stories. Just break out Excel. Speaking of, let's look at some Excel. That's the topographic factor. That's if you have a building on a super tall hill, and so for our sake, we're not going to consider that. Any other questions? Okay. So this is an Excel sheet that I posted on Blackboard. So I have here a base wind speed of 106 miles per hour. I plug in the gradient height and the exposure constant, and you can see how the computation is pretty straightforward. Keep in mind this second row here, this was our row. And I mean, you can see it's everything that we just computed. We got a KZ value of 0.766, and then we got a QZ of 18.73. And so you just repeat that over and over again, for each story. Yes? That's a great question. And so the answer is pretty much yeah. Here, let me see if I can draw this over here. So what you'd have is you'd have sort of a pressure distribution like that, and then for the fourth story, maybe it looks like that, and then, like that, and so on and so forth. So yeah. Yes? Yes. Yes. And so each story is going to have a different force. So think if let's say you had a brace frame, right? So you have a frame and then you've got, like a truss. Each joint on each story would have a different point load on it. Yep. That's a good question. So everybody else okay with this? Yes, sir.
Your KZ on the first story, or sorry, the second story is going to be different just because you're less than your Z value is going to be different, right?
Your KZ quantity, yes. And your KZ quantity is going to be different on every story.
Well, you just put E as the formula for it, right? It's less than.
Yeah. So what you can do, I think on my Excel sheet, I think I think what I did is I just hard typed it in, but you could do an if statement. You could say, if your Z is less than 15 feet, here's your expression, otherwise here's your expression. And I think, if I remember correctly, I decided not to do that because I didn't want to, load a bunch of Excel lingo on you. I just want to make sure you understood the process. But it's really not that difficult. Yes? I'm fine with either. I'm fine. I'm easy. No, I don't have a problem with that. This is the one time that that it'll be easy. Homework 2 is where it gets real. It's not that bad. It isn't that bad. So I promise. Maybe. Any other questions? This is good stuff, so I want to make sure everybody's clear on this. Okay. All right. Okay. So, like I said, one of the things I wanted to mention, so this is the example we just did. One of the things I want to mention is I am only getting your toes slightly wet. We're only dipping our toes into the vast ocean that is wind engineering. There's a lot of stuff that we're not even talking about. For instance, I'm just curious if this has ever happened. Have you ever been in a building, like a tall building, and it's been a really windy day, and you open the doors, and the doors either slam shut or they want to stay open? Has that ever happened? Okay. Well, that's a very common phenomenon in wind. You really can't get around. If you have a structure that's being subjected to a wind force, dependent upon which way the wind is blowing and where the door is, you can either develop positive internal pressure inside the building, so the building's positive internal pressure blows the doors open, or you can develop negative internal pressure, so it's like there's a suction inside the building and it slams the door shut. That can change not only the amount of wind pressure that goes onto your frame, but one of the other components of wind design, which is a really big avenue of wind engineering that we're not even talking about, is how to design for components and cladding. See, take this building. There's a curtain wall of brick and windows and whatnot that surrounds the building, and that is attached to the frame. Well, those attachments and the wall itself has to be able to withstand those wind forces, and being able to properly do that is that's a task in and of itself. And like I said, I wish we could talk about this stuff. I could talk about this stuff all day, but there's a point when we got to just sort of move on. So I did kind of want to mention that. The other thing I kind of wanted to mention is what's called torsion or accidental torsion in buildings. So the example, and the example that we're talking about a building, like I'm imagining a building that's kind of like Smith, where it's just a big like rectangle going up. So that building is very symmetric. You know, it's a rectangle, so it's symmetric, right? Well, what if the building didn't look like a rectangle? What if it was like an L shape or had a weird geometry going up? Well, when the wind hits the building, if the wind's hitting it off center, the whole building wants to twist. That's unique. That takes some analysis. So the torsion that you can get on a building just from its eccentricity, where the center of mass of the building and the center of stiffness of the building aren't at the same point, and the building wants to rotate, that's a unique experience or unique analysis in and of itself. We don't have time to talk about all of this stuff, but I just kind of want to make you aware of all of the different, cases that you can deal with in wind. So any other big ticket questions before we move on? Okay. Let's talk about earthquakes. Okay. Now, one of the things about earthquakes is earthquakes are a little different. There is no earthquake monster that pushes on a building. And I'm saying that kind of facetiously, but I'm trying to illustrate how earthquakes and how forces from earthquakes are a little different. See, with wind, there is an external force applied to the building, and then we distribute that force to the structure and analyze accordingly. Well, with earthquakes, that's not the case. With earthquakes, it's not some external force being applied to the building. It's basically a result of Newton's second law. Think force equals mass times acceleration. I mean, what does an earthquake do? An earthquake basically accelerates the ground. The ground is moving. The ground is undergoing an acceleration, and that acceleration is being subjected to the building. So the way that you get your force is mass times acceleration. The building is undergoing an acceleration, and the building itself is not, light as a feather. It has some very significant weight to it. And so force equals mass times acceleration. That's how you get the force applied to the structure. It's very analogous to hitting the brakes in your car. I mean, when you're in a car and somebody hits the brakes, you fling forward. Well, imagine the whole building trying to fling forward as a result of an earthquake. That's exactly what's happening. So basically the way that this works is we sort of treat the building as if it's one big cantilevered beam. Here's the fixed on the ground, the beam, the building sticking up like it's a cantilevered beam, and we try and determine how can we apply that acceleration to the rest of the structure. So I want to talk about the general procedure for how you would handle seismic loads, and we'll get into some examples here in a sec. So the first thing that you need to do is you need to determine what's called the seismic response spectrum. And that's basically just the ground accelerations, and that's very location specific. The seismic response spectrum here in Huntington is going to be way different than the seismic response spectrum in Los Angeles or what have you. Okay? Then we're going to determine what's called the building's period of vibration. And then using these two quantities, we determine what's called the seismic response coefficient. And the seismic response coefficient, in a roundabout way, is sort of how many G's we need to consider. So here's what I mean by G's. Okay, I'm going to borrow this for a second. Okay, I won't spill it, I promise. Okay, so let's say here's the building, right? Here's the ground. Okay, so here's the building. And the building has some certain weight to it, right? Now, like I said, we take the building and we treat it as one big cantilevered beam. So imagine if I took the building and I sort of held it up like this. So this was the cantilevered end and I held it up like this. Okay? I propose that in that scenario, the building would be subjected to 1 G. Okay? Because it's just being subjected to its own weight, the weight due to gravity. Okay? So dependent upon where you're at, depending upon the building's period of vibration and the response spectrum, we would determine how many G's the building is subjected to. And so that's really what this C sub S is how many G's there are. We take the C sub S times the weight, and that tells us the total force, the total seismic force. We call that the seismic base shear because the force is going like this. Then we take that force, so we just distribute it to each floor, and then it's a lot like wind analysis, kind of sort of the same way, how you would take that wind pressure and distribute it to each floor. Well, it's kind of the same way here. And so you would just analyze and design the structure accordingly. Is everybody okay with that general process? That's kind of what's going on. So, are we good? All right. So, this is to give you kind of an idea of what we have to deal with earthquakes. In fairness, here in West Virginia, earthquake hazards really, they aren't that big of a deal. But in some areas of the country, like for instance, if you're in, let's say, western Kentucky, you can have some pretty significant earthquake hazards. The best way of explaining, because I know some people are like, well, I've never seen an earthquake, go on in that area. That's true. But if an earthquake were to go, it would be bad. So you are still designing to that same standard because it's possible, okay? And so obviously, for instance, in California, the earthquake hazards are way more extreme than we are here. Actually, one of the most interesting places to design a structure is in Alaska, because Alaska has some very significant earthquake hazards. A lot of the structures that you're designing in Alaska, where people live, they tend to live in the coastal region. So if you're living in the coast, your wind forces tend to go up, and it's Alaska. I don't know if you realize this, but Alaska gets some snow. So in fact, they have their own snow map. So, Alaska can have some very significant environmental loads on their structure. So it's kind of interesting. What's that? This is true. But you're bringing up Geo Tech. This is not the place. Actually, no, I'm kidding. We actually are going to bring up some soil conditions here in a second. So, although it's pretty basic. Okay. Now, so I want to determine what's called the seismic response spectrum for a typical commercial office building in Huntington, West Virginia. Now, there's really no work that we need to do for this example because it's just using the website. There's really nothing to do. I do want to kind of show you what a seismic response spectrum is, and that's kind of what you're seeing here on the right. So what's on the x-axis is what's called the building's period. I'm going to talk about building periods here in a second. But basically, for now, the building period is just a unique characteristic of a structure. Based on that characteristic, whether we have short or long periods, it changes the accelerations that we have to deal with. Now, those accelerations are a function of where we're at in the country. Now, the nice thing about that website that I showed you earlier is that all of the hazards can be determined at the same location. This is actually really nice. This ATC group, they used to have different websites for snow and seismic and wind and all this. Now they've lumped it into one single location, so it's kind of nice. For instance, right here, where we put in the latitude and longitude, and we said, well, here's the wind, here's the wind pressure. We can just click a tab, and for instance, just for the sake of discussion, once it decides to load, okay, there's the ground snow load. So in our area, we would design for a ground snow load of 20 pounds per square foot. If we go to seismic, we get a report that's a little bit more detailed. Okay? Now, remind me for this example, what was the risk category? 2. Okay, so we're in risk category 2. And the site class, what was the site class? What did I say for the soil? Stiff soil. Okay, so I think it makes sense that the amount of acceleration that gets transmitted from the earth to, let's say, a given structure is going to be dependent upon the type of soil that is at that given site. In other words, I don't think that clay would transmit the accelerations in the same manner as like a dense rock would. So the soil characteristics do matter, but pretty much from a 30,000 foot view as far as we're concerned. And so if you go into the site class, there's a series of them. Stiff soil is essentially the default. So once it decides to load, and bam. So here's the seismic response spectrum. So here's our design response spectrum. And if you look at the number of Gs, we're talking about like 0.15 Gs, 0.1 Gs. That's very, very low. That's not much acceleration. But I think that makes sense because we're talking about Huntington, West Virginia. To give you kind of an idea, I put some images here in the PowerPoint. So this is, I just picked a site class just to do a similar comparison. I did an analysis of what would be the design response spectrum if we were in New York, New York, or if we were in Los Angeles. Just look at the change in the axis. Look at the amount of Gs that you would have to consider if you're in, let's say, New York, so up to maybe like a quarter, up to maybe like 1.6. It's a very significant difference in the amount of accelerations. And one other thing to consider, we are only looking at risk category 2. If we were to bump this up to, say, risk category 4, those accelerations would, because remember what risk categories mean. Remember, a risk category 2 structure is just a regular old office building, whereas a risk category 4, we're talking about, I mean, goodness, we're talking about a police station or a fire station. So those risk categories can really cause those accelerations to jump up quite a bit. So, any questions about this? Now, like I said, one of the things about this response is that it's a function of the building's period. And I said up until now, the building's period is just a characteristic, and I really didn't explain what that means. Well, now I kind of want to take some time and explain that. All right, so how many of you have ever played a guitar, a bass, a stringed instrument, or seen a guitar played in your life? Okay, there we go. All right. Now, one of the things about a guitar is this. Let's say, I didn't bring one with me. I apologize. But let's say for the sake of discussion that I had a guitar in my hand. Whether or not I take that guitar and I play a string, let's say, very softly, or I play a string with some significant force, ultimately it makes the same note. It's still the same note. It might sound a little rougher or a little louder, but the actual note, whether it's an F flat or whatever, it's the same note, right? Make sense? Okay, there is a reason for that. Okay, when you play a guitar string, what happens is this. You have the string, and you take that string and you make it undergo a force displacement. And then you let it go. Like if I had a guitar pick, I would force the string to displace, and then I let it go. Once that pick leaves the string vibrates, right? Make sense? Well, once that string vibrates, it then undergoes what's called free vibration. In other words, it's vibrating by itself. There's no additional force on it. It's just vibrating on its own. And one of the fundamental rules of structural dynamics is that under free vibration, all structures vibrate at their own natural frequency. It's why whether or not you play a string very softly or you play a string and you wail on it, you still get the same note because it's still vibrating at the same frequency. Okay? And so natural frequency, if you ever take a course in vibrations or structural dynamics, natural frequency is the day one lecture. It's the first thing that you are tasked with determining. Excuse me. So frequency is essentially how many times it's vibrating per second. So a frequency, if you had a frequency of 40 hertz, it would be vibrating 40 times a second, right? The building's period is just the opposite of that. It's how long it takes the structure to undergo a period of vibration. Now, what the hell does this have to do with earthquakes? Well, it's because what do you think's happening to the structure once the earthquake is what's happening? Well, you're taking the structure and it's undergoing a forced vibration. Once that earthquake is over, the building is vibrating under its natural frequency. So the determination of that natural vibration period is incredibly, incredibly important. That period is, and that quantity is one of the most fundamental measures that we use, not just in earthquake engineering, but in dynamics engineering, period. No pun intended. I said period again. Now, the computation of a building's period of vibration, I mean, in reality, and trying to do it explicitly is difficult. I mean, you got to break out the finite element analysis software. You got to, I mean, really break out some somewhat complex mathematics. And engineers, I've learned this. For some reason, engineers don't really like to do complex math. I never really understood that. It's like, how do we solve a differential equation? Wolfram alpha, that's how we do it. Never understood that. No, but in all seriousness, breaking out, a complex, finite element analysis for every single building that you design is a little bit unrealistic, and that's where the code comes into play. The code offers a series of simplifications depending upon what type of structure that you're looking at. So, for instance, if you're looking at a moment frame, you can determine an approximate period of vibrations. That's what T sub A is. T is the time that it requires to undergo a cycle of vibration, approximate, T sub A. It's pretty straightforward, and it's just a function of some curve fit constants and the height of the building, essentially, the structural height. So it's pretty straightforward. And so for moment frames and for braced frames, that changes, because whether or not you have physical braces between the beams and the columns, or you're using rigid connections, that changes how the building behaves. So if it changes how the building behaves, I think it stands to reason that it changes how the building vibrates. So just something to keep in mind. Sound good? Okay, so based on that period of vibration and whatever your response spectrum is, you can determine how many G's the building has to be subjected to. Now, I'm going to be honest, I am sort of glossing over this a little bit because there's a lot of stuff I'm not talking about, because going from your building's period of vibration and the response spectrum to CS is a little involved. There's an overstrength factor, there's an R factor. I'm not even talking about that stuff because that's stuff for another day. But suffice it to say that that's pretty much, what we need in order to perform this computation. Once we determine the number of G's, however, the actual distribution of forces to each story is pretty straightforward. Okay, there's a pretty straightforward plug and chug expression. It is a function of a couple of things, though. We do need not only the height of each story, but we need the weight of each story. We need to know how heavy a given floor is. A building's vibration characteristics are a function of its mass. So how heavy each story is actually matters. We also need the story height, the total base shear, and a distribution constant. Let's see what time it is. 11:48. Okay. So what we'll do next time is this. I want to show you how you would distribute earthquake forces given a seismic response coefficient. And that's what we will do Friday, so we'll spend some time doing that. Then, just so you're aware of where we're headed, I kind of want you all to see this, we're going to briefly review some stuff from concrete, some dead loads, live loads, snow loads. What's that? What? That was the unit weight of steel and concrete. We'll get there. Dead loads, live loads, and snow loads. And then after that, just so you're aware, after we finish that, we're in steel land, okay? So the point I'm making is after this, start bringing your manual, okay? Because we're going to need it. That's all I got, guys. I'll see you on Friday.